Here's a strange fact about one of the biggest discoveries in modern physics. The thing scientists spent decades chasing lasted about 2/10 of a second. Not 2/10 of an hour, not 2 minutes, 2/10 of a single second. Blink and you would miss it. And when it finally arrived, the first reasonable reaction was not, "we found it." The first reaction was, "this is probably noise." To understand why, start with a prediction. General relativity says something genuinely bizarre about gravity. Mass does not just sit in space, it bends space. And when massive objects accelerate, when they move violently, they send ripples spreading outward through the fabric of spacetime itself, stretching and squeezing everything they pass through. Those ripples are gravitational waves. The theory was confident they existed. The trouble was the size of them. By the time a wave from some distant catastrophe reached Earth, the stretching and squeezing it caused would be vanishingly small, so tiny that catching it would demand instruments of almost absurd sensitivity. So physicists built exactly that. Enormous, extraordinarily delicate detectors, waiting in silence for a tremor from somewhere out in the universe. But here's the catch that defines this whole story. A detector that's sensitive does not only feel gravitational waves, it feels everything. A truck on a distant road, a small earthquake on the far side of the world, a shift in temperature, a flicker in the power grid. The machine is swimming in tiny disturbances all the time. So when a promising signal finally appears, seeing it is the easy part. The hard part, the part that actually earns the word discovery, is proving that what you saw came from space and not from the world shaking around your instrument. One detector noticing something odd proves almost nothing, which brings us to September 14th, 2015. On that morning, both of the advanced LIGO observatories registered something, not one of them, both. And the shape of it was exactly the kind of thing to make a physicist lean in. The signal swept upward in frequency, climbing from around 35 hertz to about 150 hertz in roughly 2/10 of a second. Rising pitch, faster and faster, and then gone. If you translate it into sound, it was a chirp, a quick upward whoop. And that rising pattern was not arbitrary. It is the signature you would expect from two heavy objects locked in orbit, whipping around each other faster and faster as they spiral closer, right up until they collide. So there is already a temptation to celebrate. Two detectors, the right kind of signal, the predicted shape. But two instruments seeing something similar at nearly the same time is not proof. It could be coincidence. It could be some disturbance that happened to rattle both sites at once. At this stage, a promising signal is still a suspect. And the next question is the one that begins to separate signal from noise. Did it arrive at the two detectors in a way that actually makes sense for a wave sweeping across the planet? The two LIGO sites sit far apart, near opposite ends of the country, one in Livingston, the other in Hanford. If a real gravitational wave washed through the Earth, it would reach one site first and the other a moment later. And that delay is not free to be anything it likes. It is fixed by the distance between the detectors and the speed the wave travels. So what did the data show? The signal arrived at Livingston about 7 milliseconds before it reached Hanford, 7/1000ths of a second. And that gap is exactly what you would get from a wave crossing the continent at the speed of light. Sit with what that one number does. It quietly kills an entire family of dull explanations. If two unrelated local disturbances had simply happened to look alike at both sites, there would be no reason on Earth for them to line up with that precise light speed delay. The timing says this was not two coincidences that resembled each other. This was one thing, moving, passing through one detector and then, a heartbeat later, the other. Something had crossed the continent, but crossing the continent still is not enough. Fine, a real wave passed through. Is it the kind of wave the theory actually predicts? Because a wave being real and a wave matching the mechanism are two different claims. And here both speed and rigor mattered. Within about 3 minutes of the signal arriving, an automated rapid search had already flagged it. And notably, that fast search did not need to know the exact waveform in advance. It could catch the candidate from its structure alone. But flagging is not confirming. The deeper test came afterward, when analysts took the recorded signal and compared it against enormous banks of waveforms calculated ahead of time from the theory, the precise shapes that compact objects should produce as they spiral inward and merge. That matching technique is like holding thousands of predicted fingerprints up against your signal to see whether any of them fit. One did. The data lined up with the predicted pattern of two compact objects and spiraling together and closing in. Now the signal is not just a wave that crossed the continent. It is a wave whose detailed shape matches a specific physical process. But, and this story runs on the word but, matching a prediction is not the same as ruling out every earthly cause. What if some disturbance here on the ground had just happened to produce a wiggle that mimicked a merger? So the collaboration went hunting for exactly that. This is the part people rarely imagine when they picture a great discovery. Not champagne, but a determined, almost stubborn effort to destroy your own result. They pulled the records from the monitors surrounding each detector, the seismic sensors watching the ground, the temperature logs, the power grid records, the diagnostics tracking each machine's own quirks. They were looking for anything, any disturbance at all, that could have pushed that signal into both instruments. They found nothing that fit. No tremor, no glitch, no power fluctuation that could plausibly explain what both detectors had recorded. That is a powerful result. But notice its limit, because the scientists certainly did. "We found no disturbance that explains it" is not the same statement as "no disturbance could ever explain it." There's always a nagging possibility left over. What if some unknown, unlucky pileup of ordinary noise had, by pure accident, faked the timing and the frequency sweep and the waveform all at once? You cannot chase down a cause you cannot even name. But you can do something else. You can ask how likely an accident like that really is. And this is the final gate. You took the detector's own noise, the ordinary background hum these machines produce constantly, and studied how often that noise, entirely on its own, could throw up something resembling this event. The answer is the number that closed the case. An event like the one they saw should be mimicked by random noise less than once in about 200,000 years of running these detectors. Less than once every 200,000 years. In the language physicists use, that is a significance greater than 5 sigma, comfortably past the threshold they traditionally demand before anyone is allowed to say the word discovery. Be careful about what that figure means, though, because it is easy to overstate. 5 sigma is not a measurement of how true the theory is, and it does not announce that the universe is definitely one way rather than another. What it says is narrower and more useful. The odds that mindless noise conspired to produce all of this all at once are staggeringly small. And that is really the heart of the whole story. No single test here was bulletproof on its own. Dual detection could be coincidence. The timing alone could be a fluke. A waveform match could be wishful pattern hunting. But to explain this signal away as noise, you would need every one of those independent tests to fail in the very same direction at the very same moment. And the statistics say that is essentially impossible. Each constraint by itself leaves the door open. Taken together, they close every door but one. So what walked through the one door left open? What actually made this wave? When the analysts read the waveform closely, the way it rose, the way it peaked and then rang down, it told them about the objects that produced it. 2 black holes, one around 36 times the mass of our sun and the other around 29, had been trapped in a death spiral, circling each other faster and faster until they merged into a single black hole of roughly 62 solar masses. The chirp climbing from 35 to 150 hertz was, if you like, the sound of black holes finding each other and becoming one. And that is the moment the whole thing clicks into place. This was not an abstraction anymore, not just a squiggle in the data. It was a specific, violent, ancient event, 2 of the strangest objects in the cosmos colliding, reconstructed in detail from a signal that lasted 0.2 of a second. There's one more reason this mattered, and it reaches far beyond the single event. Until that morning, gravitational waves were a prediction, confident, elegant, but never caught directly in the act. Afterward, they were a fact you could point to. It was also the first direct evidence that black holes can pair up and merge, something the theory had allowed but no one had ever witnessed. And it opened a genuinely new way of sensing the universe. For all of history, astronomy had essentially meant gathering light, visible light, radio waves, X-rays, different flavors of the same electromagnetic messenger. Gravitational waves are not light at all. They are tremors in space-time itself, and they carry news of events that give off little or no light, like 2 black holes colliding in the dark. A brand new sense had come online. It is worth sitting with how this discovery was actually made, because it cuts against the cartoon version of science. There was no single instrument that lit up and announced the answer. The detection was earned. A 0.2 of a second chirp showed up looking, at first, like it might be nothing, like noise. And it became one of the defining discoveries of the century only by surviving a gauntlet, appearing in 2 separated detectors, arriving with a light speed delay that ruled out coincidence, matching in fine detail the shape the theory predicted, showing not a single fingerprint of any earthly disturbance, and finally passing a statistical test so severe that chance was left with nowhere to hide. Not one of those tests would have been enough alone. Any one of them could have exposed a mistake. The signal passed all of them, and when every independent line of evidence points to the same answer, and the ordinary explanations have been eliminated one by one, then whatever is left standing, however extraordinary it sounds, is simply what happened.